In this video, we're going to do another homework problem from Experience 11, in which we are doing a hypothesis test regarding a population proportion. Test the claim that the proportion of people who own cats is significantly different than 60% at the 0.1 significance level. Okay, so let's pick the appropriate set of null and alternative hypotheses here. Now they've given us some options regarding the letter P and the letter mu. None of the options with the letter mu will apply because we are looking at the proportion. So we can single out all the ones with the letter P. And furthermore, we want 60% to be the hypothesized value in the null and alternative hypothesis. They all have 0.6, so we can't single anything out there. But now we want to see, is our alternative hypothesis left-tailed, right-tailed, or two-tailed? Because we're seeing if the proportion of cat owners is significantly different than 60%, that implies a two-tailed test. It is not necessarily looking for a percentage that is less than or greater than 0.6. It's looking for a difference. Now we're going to calculate the test statistic and then the p-value based on this sample information. So let's write down this info in our little writing space over here. The hypothesized value for the proportion, that's p0, that's the 0.6. We've already given that info up here. The sample size is 600 people, so that's n. The proportion of that sample who owned cats was 59%. In this example, they have already computed p hat as a decimal. So they didn't say it was, 59 out of 100 people. They already computed this as a decimal. So that's kind of nice. I'm going to undo that. But now we can go and insert all this info here into our test statistic and do some computations. So our test statistic starts with the sample proportion, 0.59. And we are seeing how different that is from the hypothesized proportion of 0.6. And in the denominator, 0.6 times 1 minus 0.6 over n, which is 600. Lots of sixes. Okay, I'm going to open up our calculator so we can compute this. Okay, I have whipped open my calculator and I have started typing away the numerator. That's an easy one. The denominator, we've got a big square root, 0.6 times 1 minus 0.6 divided by 600. Ooh, that's a very nice number. We've got now a negative 0.01 divided by a 0.02. We could probably do that without the calculator, but I'm going to do it anyways. Negative 0.01 divided by 0.02, definitely a half. So negative 0.5. That is our test statistic. I'm going to go ahead and put it in a circle. But now our next step is to compute the p-value. To do this, we need to use our z-table. So I'm going to open up our z-table in a moment, but before I do so, I want to draw a picture. I think these pictures are very valuable, so that way we know what to do when we open our z-table. We are working in the z distribution. our test statistic was a negative 0.5. Think about that as a z-score. That's not an incredibly large z-score. When we determine the probability beyond negative 0.5, that is going to be this area in pink in the tail beyond negative 0.5. Now here's the thing though, this was a two-tailed test. So we also want to find the symmetric area over here, which would be the area to the right of this tick mark, positive 0.5. Now we didn't calculate positive 0.5 as our test statistic, but because we're looking for a difference, we can observe a difference in two ways, right? Something can be different by being larger or considerably smaller. So we kind of look in both directions. Now, how do we find this area? I need to go to the z-table. This tick mark, the negative 0.5, that's just like a z-score. So we're going to look up that tick mark to find these probabilities in pink. Okay, I have acquired my z-table here, and I'm going to look up in this first column for negative 0.5. Here it is, negative 0.5. Now there is no second decimal place value there, right? So I want to stick to the first column here that says 0.00. The intersection of this row, that column, is 0.3085. So that is our answer for one of these areas in these tails, 0.3085. But that's not the entire answer for our p-value, because this pink area over on the right side is also 0.3085. So we want to go, so let's go to our calculator and multiply 0.3085 by 2. And that is going to be our p-value. It is 0.617. Now that we have our p-value here circled in yellow, we are ready to state our conclusion regarding our set of hypotheses. We want to ask ourselves, what is alpha? It was given in the problem as 0.1. And really we need to consider the comparison between our p-value and alpha. So our p-value, approximately 0.6, is that bigger or smaller than 0.1? Certainly bigger, right? Therefore, our conclusion will be to not reject the null hypothesis. Or we can say we fail to reject the null hypothesis. In addition, I like to consider, what does that conclusion, failing to reject the null hypothesis, what does that imply about this proportion? When we fail to reject the null hypothesis, what we say is that there is insufficient evidence, or there is not sufficient evidence in support of the alternative hypothesis. Essentially, a non-rejection of the null hypothesis is sort of giving credibility to the null hypothesis. We're not proving it, but we just do not have evidence against it. So we'll say that there is not evidence that P, the proportion of cat owners is significantly different than 0.6. So there is not sufficient evidence that the proportion of cat owners is significantly different than 60%, period. If our conclusion was completely different, let's suppose our conclusion supported a rejection of the null hypothesis. If our conclusion was completely different, I would just wipe out this one word that I'm underlining here. And that can help you structure your conclusions or interpret a conclusion that is already pre-written. Let's go type these values in to make sure that we are correct. Our test statistic, -0.5, p-value 0.617. Oh, they want us to round to 2 decimal places, 0.62, and we failed to reject the null hypothesis. Okay, I hope that helps. See you in the next video.